In this last section of the chapter, we're going to talk about Schrödinger and Heisenberg and what their contributions were to quantum mechanics. So he's best known for the creator of being wave mechanics and worked on problems of general relativity, cosmology, and applications to quantum mechanics to biology. So Schrödinger came up with the wave equation that describes all matter in how waves change in space and time. The Schrödinger's wave equation, which you'll probably get to if you're going to take physical chemistry, is a key element of quantum mechanics, and it's typically given the function phi. It's beyond the level of mathematics that we're going to do in this class, so we're not going to talk about it, but it is a fun equation to solve. So the wave function depends on the particle's position at any given point in time, and the value of phi squared at some location is the given time is proportional to the probability of finding the particle at that location. So we'll find that when we start getting into quantum mechanics that we're not talking about where something is we're going to talk about where the probability of finding it is going to be. So this is where Heisenberg came in. He made his contributions when he was quite young. He just basically created matrix mechanics and won the Nobel Prize for the uncertainty principle. And he made many atomic and nuclear models and forms of molecular hydrogen. So he's most famous for the Heisenberg uncertainty principle, when he basically said when measurements are made, the experimenter is always faced with experimental uncertainties in these measurements. And so classical mechanics offers no limit to how good we can make our measurements and would allow for arbitrary small measurements. But quantum mechanics predicts that there's a barrier to these measurements and how small we can actually measure something. And he introduced the Heisenberg uncertainty principle, which basically says that if we make a measurement of a position of a particle is made with some precision delta x, and a simultaneous measurement is made of its momentum or its speed at some other position, then the product of these two uncertainties can never be smaller than this value. So mathematically, that looks like math, right? We're going to write it this way. So delta x, the uncertainty in x and the uncertainty in p, the product in those can never be smaller than this value, where again, that's Planck's constant. It's typically impossible to measure simultaneously the position and the speed then of the particle. And that's how you might hear this said, is we can't measure both things at the same time. So another form of this principle deals with the energy and time, that we can basically transform the equation. So what does that mean? Is that in order to observe an electron, we have to bounce a photon off of it. And in bouncing that photon off of it, we've interacted with it and changed it somehow. So we can't simultaneously know for sure where its speed and position are at the same time. So basically the uncertainty principle views the electron as a particle. Its position and velocity cannot both be known, and its energy can be uncertain for a period of time given by this. So we're going to resolve the equation for delta T. Okay, so let's use this mathematically. So an electron passes through a small slit. So we're going to do a diffraction experiment with this width. What's the uncertainty in the electron's momentum component in the direction perpendicular to the slit, but in the plane containing the slit? So then we can use our uncertainty principle. H is again 6.626 times 10 to the negative 34th joule seconds. And then divide that by 4 pi. And the uncertainty is going to be half of this. We're assuming that it went through. So it's going to be 1.0 times 10 to the negative 8th over 2 meters. And then we get 1.1 times 10 to the negative, so it's kilogram meters per second is the most precision we can have on that measurement.